Hi everybody, yeah, as Chris says, James Douglas, or Jim Douglas to a lot of people that I know in the industry. I'm the former Chief Surveyor for the ATC system-wide contract on Crossrail that would put the systems infrastructure to the central tunnelled section. I was employed by Alstom Transport. Our partners in that JV were Crossrail and TSO, the specialised track builders. So I'm going to talk to you today about a paper I submitted to the conference, Automated Drilling for Installations Inside the Crossrail Tunnels. This was solving the problem of drilling into the civils infrastructure in order to install the system-wide services that would make Crossrail operational. So what was the challenge? This is actually the Crossrail tunnel as fitted out now. There's a Crossrail train sat on the tracks there. Our role, as well as installing the track, was to put in the services around that track, and these the letters at the top. We've got obviously mechanical and electrical, overhead line, the walkway, which was for emergency purposes, and the cable management system carrying signalling and other power and lighting systems. What's the challenge? Well, on these sorts of infrastructure projects, certainly the experience on HS1 or Channel Tunnel Rail Link, as it was known, was that in order to install the services, we needed to drill into the tunnel lining. And drilling into the tunnel lining presented three challenges. You had the safety dimension, working at height, dust, confined space. You had the need to solve the interface with the so-called no-drill zones. You can't drill close to the edges of the segments or into the grout holes or bolt pockets. And thirdly, the positioning of these drill holes is complex. It's not like fitting out a building or something where the lines of services are unmoved. We actually had to rotate and shift the services to suit the position of the track and the train. In the past, how was this done? Well, it was teams of manual operatives being led by a lot of engineers, a lot of trial and error, iteration, uncertain phase of the works in terms of time completed because of the need to refer to the overall scheme of the layout if installations couldn't go where we wanted them to. So just referring back, the health and safety dimension, hand-arm vibration was also seen as a big challenge, drilling into concrete lined tunnel to a fixed depth, drilling upside down and at height. And of course the trial and error dimension, we had these no drill zones, which I'll explain in a moment, services rotating, an iterative process, and by golly, there was a lot of it. There was 42 kilometres of tunnel and 250,000 holes that we had to install to the correct position and depth. Okay, so very briefly over board tunnel arrangements for those who are not familiar with the tunnelling industry. It's 8 segments in this particular configuration, 6.2 diameter tunnel, 5 standard segments, a key segment that's used to lock the 1.6 metre long ring in place, 2 counter key segments known as the shoulder. Now these segments can fall anywhere in the round the clock of the tunnel, and the reason for that is that the segments are tapered and used by the tunnellers to go in different directions. So basically, as they rotate the key into a different position as they build the next ring, they can turn the tunnel to the left, right, up or down. And of course there were a number of other phenomena at play. The machine obviously had tolerances and movement, and phenomena like the machine rolling would introduce hundreds of millimetres of change in any design position. We've got the features that had to be avoided: the pocket, the grout hole, circumferential dowels. Here's the no drill zones graphically illustrated, 20 to 30% of the surface area. And as I say, in this case, actually just 3 segment types to consider. Here's the no drill zones in the context of the tunnel. A number of rings are blended together to show if the tunnel was unwrapped, how the node drilling area would look. And what were we installing? Let's just concentrate on the detail of that. The overhead line equipment, 3 holes every 9.6 meters, cable management system on the right hand side. You can see a 3.2 walkway and fire main bracket, the earth wire for electrical safety, cable management system on the left hand side. An awful lot of holes that needed to be installed very precisely. These services rotated with the train position on the track, and perhaps this is the moment at which I introduce the idea, which mathematics of which are discussed in the main paper, the difference between the tunnel as it was built and the design tunnel alignment, which is the centre of the tunnel as designed, which has a relationship to the track centre line. So basically these two centres of the tunnel continue to coexist. The BTM, which it governs where the train will be, the track is actually built to, and then between that and the BFC, or the best fit of the tunnel, you have a tolerance. In Crossrail's case, it was 100 radial millimetres, so it could be made up of difference of a horizontal and vertical component in 2 dimensions, looking at the ringing cross section. I want to go through the logic of the computer program in terms of what we needed to do for a drilling machine solution. If you can consider the walkway bracket here, the original design, or if you first iteration, would suggest that we had 4 fixings to attach it to the tunnel lining, and in this very first case, happily, the fixings happen to be clear of the no drill zones. But of course, what as likely, perhaps more likely, is that on any other ring, that same bracket installation wouldn't work. So we have a situation where you could move the bracket closer to the previous bracket. You couldn't move it further away because of the structural and strength requirements for the bracket fixings. But in terms of solution, you're already looking at the need for extra holes. So extra holes, and in order to create a series of acceptable permutations, we asked the design team to consider a series of holes, more holes than were needed, a number of permutations. I believe for the walkway bracket there were 20 different permutations, 4 fixings required. Of course, what we needed the computer program to do was to assess the positions of no drill zones, use the input information for the bracket, and come up with one of the permutations. So no deliberation on site, basic selection. If in cross-section it couldn't be solved, then the secondary function for the program was to shift the bracket longitudinally. Of course, what that does is create knock-on effects, and their computer program worked, from the whole to the part in order to deliver an overall solution for each of the drilling runs. What did this project also yield in terms of technology for surveying? Well, in terms of 3D laser scanning, which has been around for 20 years, certainly it came up with a very efficient way of delivering the output model from the scanning. So what we did was we were able to take the ring, produce a wireframe for that ring. There's a number of wireframes there that have been overlaid on the point cloud of the tunnel. But the key thing was that we projected the 3D point cloud to a 2D plan, very simple mathematics to do that. We then were able to overlay the unwrapped wireframe of the ring with the key segment, line up the key segment to where the point cloud showed that it was, rewrap, and what you had was an instant wireframe modelled out of the point cloud, saving significant amount of time in manual modelling, which is often the limit point to surveying with scanners. And of course, if the segment join was unseen, and there were line issues with scanners in tunnels, the segment pattern could match to the key segment, enabled us to model segments that were unseen by the scanning. Okay, so very small bit of mathematics, but very quick to understand. Easting Northing's height, what you see on an OS map Obviously engineering grids slightly different, but they use the concept of eastings, northings and height. We transformed that to X, Y, Z. XY being the 2 dimensions in the 2-dimensional plane in cross section, Z being the distance along the tunnel. And then furthermore, in order to make it fit with the concept of a drilling machine that needed to know its distance along the tunnel and an angle from its zenith in order to make a drill, we transformed X, Y, Z to Z and theta. Very simple mathematics. 3D ENH to 2D XY with a Z component, and basically Z and theta were used to map the segments and drilling permutations. You can see in the bottom left-hand corner the concept for the Cartesian system. So, okay, data processing. We had to develop a computer program, take all the drilling rule books that were created by the designers, test those coordinates, test for clashes, and basically produce a resolved drilling plan. We needed a partner. We went looking for Costain and Alstom's preferred partner in the business, Enable My Team. I'm happy to say the CEO and founder of Enable My Team are here, and with their experience from previous projects and their undoubted computer programming ability, we were able to produce the computer program for the necessary outputs. And really, what were the program outputs? The program outputs were very simple: a distance along the track from a known reference point, an arm selected on the drilling machines, an angle from the zenith, a location of one of the drills on the drilling arm, whether it was on or off, and if there were successive epochs from the same stabled position of the machine, the selection of that arm for that epoch. Here's the drilling sequence. I'm really running through this, so I'd like to show you a video very quickly. Here's the drilling machine with the inclinometer measuring from, you can see the chainage angle extension of arm, drills on and off, and the concept of the drilling arm rolling up and down the static machine. Here are the machines as they were constructed. There were 2 dedicated machines, one for the walkway and CMS, one for the OHLE and the earth return. Why was that? We wanted the drilling arms in the correct places in order to effect the most optimal drilling. So there were 2 machines. The Z-axis, we used a target plate reference to the track control, and for the X and Y control, remembering the BFC to DTA relationship, the mathematics between the BFC and the DTA were resolved. The machine found itself in the true center of the tunnel using hydraulics that basically needed to be equilateral, and some very simple vector control by lasers. Okay, production and accuracy. We sent survey teams to the front, basically to use the mathematics that were already in play to take those measurements to assure that the machine was calibrated. Typically 1 centimetre, in chainage 2 to 3 centimetres. We can talk about that if somebody fires a question at me. And the production rates, 200 metres per shift, were achieved. The lead engineer, Tim Kelly, who was part of the 3-man team that really delivered this, along with myself and Sandeep, the programmer. Tim Kelly was the M&E lead engineer, and he basically was able to show that we achieved the work of 20 operatives, excluding the setting out, the iterative trial and error process that would have been involved with marking for manual drilling. Tayan, can you just quickly fire the video up if we have time? I think it puts into pictures my words.
So we're in the Thames Tunnel, the Crossrail tunnels approaching Woolwich Station. The drilling machines are designed so that we can drill all of the holes into the tunnel lining to fit all of the services, such as the emergency escape walkway, the cable management systems that carry all of the power, and the overhead line that powers the actual trains themselves. So this is first of its kind in the world, this machine. We have 42 kilometres of tunnels in the Crossrail project. The holes that we're drilling here are for the services. Holes are drilled in roughly every other ring. We have about 16 holes per ring. That figures out about 250 to 300,000 holes across the entire project. So in advance of the drilling machine actually carrying out the physical work of drilling the holes, there's 2 phases. The first phase is a 3D scan. So the 3D scan takes measurements along the tunnel at very small increments. It highlights key features. Once we have this data, it's laid out into a coordinate form, and then there's a computer program which essentially lays segment templates out into a line, plots the hole positions for the brackets, and then allows us to check where the holes need to go before being input into the machine. Once they're input into the machine, then the machine can go ahead and drill the holes themselves. There's the fact that we no longer need to set out the holes in advance. So traditionally, a surveyor would have to go along the tunnel, physically mark every position, for then someone to come in and manually drill it. The labourer and the guys aren't actually in physical contact with the tools, so they don't have the vibration through their arms and their hands. This machine uses a predefined set of coordinates and the guidance so that it can actually come in and drill the holes just from single target references. So the target output of the machine is around 200 to 250 metres each shift. We have all 42 kilometres to do, so we're now focused on getting the machine through these tunnels as quickly as possible, making sure that we've got everything right first time and we don't have to come back and rework again afterwards. So the machine moves itself in the tunnel using one of two modes. So we have the railway mode, so running directly onto the rail, and we also have a road mode, so we have road wheels which fit onto the vehicle and allow it to move in the tunnels before the track has been laid, as well as now in this situation where it's already in. So once we have the machine inside the tunnel, we put some guide rollers out to come in contact with the tunnel lining. The purpose of these guide rollers are to make sure that the centre of the machine aligns with the centre of the tunnel, so that as the arms rotate, they're rotating around the middle, and then when they extend out, it makes sure the holes are in the correct position and the drills are perpendicular to the tunnel lining. Going forwards, this sort of production line thinking approach can be taken to more of the construction and the railway industry. It's a method we can use to make things safer and faster, and ultimately save time and money in large-scale projects such as the Crossrail programme.
Okay, Tim, thanks for making my conclusion there. Thank you very much for listening, and I guess Chris will ask if there's any questions.